Good afternoon, good morning to everyone attending today's webinar. My name is Drew Buchanan. I am the engineering manager here at True Insight. Really happy to have everyone here. For today's webinar, we actually have a guest host leading the webinar. So I'm going to introduce Eric right now. For those who don't know Eric, senior application engineer at Altair, very talented in the EDEM and discrete element modeling world. So happy to have you, Eric. I'm going to hand it over to you now.
Yeah, thank you, Drew. Can you hear me clearly?
Yep, loud and clear. Thanks, Eric.
Perfect. Well, hello, everyone. It's my pleasure to have you here today. Today, you'll learn how EDEM is used in designing construction in mining heavy equipment. My name is Eric Beichel. I'm a senior application engineer at Altair, and I'm joined here today with Drew from True Insight. Please feel free to send your questions during the presentation in the chat. Drew will do his best to answer the questions during the presentation, but for any questions that are perhaps more on the technical side relating to EDEM, I'd be happy to answer those at the end of the presentation, where I expect we'll have something like a 15-minute or so Q&A session. So bulk material handling problems are everywhere in industry, whether it's in a quarry where rocks are being moved, crushed, and grabbed, or in a mining where overburden or ore is being excavated, transported, and processed. Over 70% of industrial processes involve granular materials. Traditionally, most of the bulk materials handling and processing operations, including mobile equipment, are empirically designed, and the measurements of input data into models such as force and pressure on equipment is difficult to obtain, time-consuming, and costly. Typical bulk material problems faced include things like blockage, material buildup, equipment downtime from broken parts, equipment wear, that all ultimately lead to lower productivity. This webinar is designed to let you know more about the advanced capabilities that combines the bulk material handling simulation abilities of EDEM and finite element, computational fluid dynamics, and multi-body dynamics analysis tools of Altair OptiStruct, AccuSolve, and MotionSolve, and other CAE software. In today's webinar, I'll be covering the following topics. First, I will give you an overview of some of the challenges that are involved in designing heavy equipment, which I imagine everyone that attending this webinar is intimately familiar with. Then I will introduce some of the key simulation technologies provided by Altair and discuss some of the key benefits and how these technologies can be integrated with other CAE tools in design processes. To demonstrate these software capabilities, I will showcase some typical real-world applications. And finally, we'll wrap up and give you an opportunity to ask some questions. Manufacturers of heavy equipment are faced with a wide range of challenges. To meet the demand of the market and stay competitive, manufacturers need to continuously improve their performance, efficiency, and reliability of the machines, but also deliver products quickly while ensuring product innovation. This means shortening the design cycle, and getting it right the first time is critical. One challenging aspect relates to the range of operations and conditions that machines have to perform in, while another significant aspect is the range of materials that the machines have to deal with. Vehicles like skid loaders, excavators, backhoe loaders, or truck bodies are all intended to handle bulk materials that can vary in shape and form, from large quarry rocks to cohesive soils, abrasive ores, or free-flowing sand, to mention just a few. These materials and their interactions with the machine parts have a strong effect on the equipment performance. Materials like sand, gravel, rock, soil, ore have very diverse properties, which can vary by location and by environment. Not only are bulk and ground materials highly influential on the performance of the machine, but they're also complex in their behavior. These materials vary greatly, both in terms of the size of the particles, for example, sand versus larger stone or gravel, which will react in different ways. Also because the behavior of these materials can vary based on factors like moisture content or the degree of compaction. Take a material like sand, for example. It can be dry and free-flowing and behave in a way that is more like a fluid than a solid. However, after a period of heavy rain, the moisture content increases and the material will become more cohesive and sticky. It'll be more resistant to motion, at least at first. And should the moisture level increase further, it may even go beyond a solid and become somewhat of a slurry. Customers demand customized solutions and confidence that the equipment will perform as expected for a range of operating conditions. Designing equipment to operate in or interact with a wide range of materials traditionally required extensive physical testing. However, physical testing is costly and time-consuming and typically restricted to a small number of available materials and tests. And this is where numerical simulation comes into play. EDEM is a high-performance software for bulk material simulation. It uses discrete element modeling, also known as DEM, to simulate the behavior of bulk material or granular materials such as coal, mined ores, soils, tablets, and even powders, and their interactions and impact on the machines and equipment. It allows you to virtually test equipment under the same condition so that you can compare different designs in the same environment and identify changes due to material behavior easily. So what is EDEM? The software itself is split into three main components: the creator, the simulator, and the analyst. The creator is where the parameters of the simulation are defined. This is done by defining the material and the equipment properties, particle to particle to geometry interactions, as well as geometry kinematics and physics models. Particle shapes are also defined here. And in the screenshot shown here in EDEM, you see a multisphered particle. Often we recommend using a multisphered approach for solving DEM simulations because of their computational efficiency. I also want to point out that EDEM has the capability of using polyhedral particles, single sphere particles, multisphere particles as shown here. And in the 2023 release of EDEM, which is imminent, we will no longer be restricted to solving with only one particle type. We'll be able to mix all of those particles together in a single simulation. The simulator is where the simulation is run. This is where parameters such as time step, runtime, and data save intervals are set. And finally, the analyst is the part of the software where the results of the simulation are reviewed. An engineer or analyst can post-process results, visualize data, create videos, images, and graphs, or data can be exported so that it can be analyzed in a different third-party software. EDEM provides engineers with the ability to model a wide range of material types. On the left, we have a rough gravel-like material, and you can see how the individual elements interact with each other. In the middle, there is a much finer dry material, more like sand, that is very free-flowing as the bucket passes through it. And finally, on the right, we have an example of an EDEM model of cohesive material. And you can see how different the behavior is with the material sticking together as the bucket moves through it, and also gives a significant greater fill level than the other cases. Of course, there are not just three types of materials out there, but this highlights what EDEM can do and why it is used by engineers around the world to model bulk material behavior from coarse dry rocks to fine cohesive powders, as well as dealing with mixtures of different material types. Whether you're an experienced analyst or completely new to DEM, we understand that it is a challenge to define a virtual model that accurately represents your bulk material of interest. To address this challenge, we have created the generic EDEM material model, or GEM database for short. And that database has over 60,000 material models that you search based on your materials, angle of repose, and bulk density. The GEM database will define all material model inputs so that you can be running your simulation in seconds. I'd also point out that there's also a starter pack that covers a wide range of different industrial applications, from agriculture and off-road applications or powder handling processes, normally applicable to pharma and additive manufacturing. These starter packs allow you to link your simulations to real-world materials. For more advanced users that would like to calibrate and develop their own material models based on physical test results, there is the EDEM calibration kit. It is a collection of EDEM simulations of standard characterization instruments that removes the need for modeling standard tests and automates the process of obtaining relevant simulation data. There are 7 available tests. We've just added the cone penetrometer kit in the 2022 version of EDEM that's not shown here on the slide. Each kit comes with an associated EDEM PI post-processing script that can be used to automate a large portion of the material calibration workflow. As you can see here, the script provides a simple, fast, and automated way of analyzing simulation data, as well as generating individual simulation reports, similar to the ones generated by physical tests. As well, you will receive collated reports of key results from all simulation runs. The kit removes the need for modeling standard tests and automates the process of obtaining relevant simulation data, leading to a significant reduction in engineering time required for EDEM material model calibration. Before we talk about the applications, I want to touch on how EDEM is increasingly being integrated into advanced CAE workflows. Altair recognizes that DEM simulations do not necessarily exist on their own, but can also fit into engineering workflows which take advantage of couplings with other CAE tools such as finite element analysis, multi-body dynamics, and computational fluid dynamics. For example, bulk material loads from EDEM can be coupled with Altair HyperMesh for use as input to an FEA analysis. This is useful for helping engineers define loads accurately in an FEA analysis when those loads are a result of the interaction with bulk materials. Similarly, loads acting on geometry in EDEM can be used to drive the dynamic motion of geometries in a number of multi-body dynamics applications, such as MotionSolve, MSc Atoms, Siemens LMS Virtual Lab Motion, and Recordine. Coupling with MBD allows engineers to better understand the influence of bulk materials, or the influence that bulk materials have on the dynamics of the machine. For example, if you're looking at analyzing vehicle-soil interactions. Finally, EDEM also offers the capability to couple with CFD software, where particle motion is influenced by the fluid phase, and the fluid phase is influenced by the solid particle phase. A two-way coupled simulation. Altair's CFD software AccuSolve can be coupled with EDEM as either a one-way or two-way coupled solution. Alternatively, coupling is also available with other CFD softwares like ANSYS Fluent and OpenFOAM. And this capability enables engineers to investigate fluid particle interaction and has applications in, for example, pneumatic conveying of particulate materials or dust emission modeling when mining equipment such as a dump truck or train wagon tippers. Later in this webinar, we will look at a couple of examples where EDEM has been coupled with other CAE software tools and talk about the advantages that those couplings provide. So by including EDEM in your design workflow, engineers are able to understand how different materials affect their designs by virtually testing a wide range of different materials. And in doing so, this allows a user to predict material behavior that is relevant for their application, helping to identify and reduce, or perhaps even eliminate risks of things like blockages, spillage, and wear. In doing this, users are able to gain insight into how different materials interact in different ways with their machinery, ultimately shortening design cycles as fewer physical prototypes need to be built and tested in order to understand these different effects. Ultimately, this means that companies that are using EDEM are able to increase productivity and reliability and design machines and equipment with greater performance in a shorter time scale than those who don't. EDEM has a wide range of applications in many different industries. In construction and mining equipment design, applications for EDEM include any bulk material handling equipment, such as dump trucks, excavators, backhoe loaders, dozers, and skid steer loaders. A number of top construction and mining OEMs have been using EDEM for many years, and consequently, they've been able to deliver better design machines on time and at a reduced cost to the customer market. I'll go through each of these examples in a bit more detail and show how users benefit by using EDEM in these application areas. Our first example is a truck body. Truck bodies typically need to load and unload material quickly and without spillage or hang up to be efficient and reduce fuel consumption. EDEM can be used to analyze the loading and discharge of truck bodies, identify areas that are subject to higher wear or areas that material will hang up. You'll see an example of this in the next slide. Users are also able to perform repeated tests under the same condition quickly. So for example, to test a slight modification to the truck body, it's as simple as bringing in new CAD model and running the simulation without having to rebuild a physical prototype. And all this combined can help reduce the number of load cycles and fuel usage, meaning energy and cost savings. This video shows some of the analysis that can be done with EDEM applied to a dump truck. In the case of analyzing the loading pattern of the dump truck, you can visually inspect the simulation and you can see in the video on the right, but you can also look at it, say the average mass flow rate of the material leaving the truck body. So the first plot shows what the unload pattern looks like for a loose dry material, while the second plot is a fine cohesive material. You can clearly see that there's a difference in the unload profiles. You can also look at the forces and pressures that the geometry is experiencing to better understand the loads on the geometry or to analyze wear. And these loads can then be exported to a FEA program to structurally analyze the body and optimize the design. This is an example of VR Steel in South Africa, who make equipment for mining industry. Using EDEM simulations as virtual prototypes, VR Steel was able to simulate the loading and unloading pattern on both the conventional load body and their new lighter design, using a variety of materials at a fraction of the traditional physical prototyping and testing cost. In terms of the numbers, EDEM helped VR Steel demonstrate that their new load body design reduced the body mass by 20%, reduced the fuel consumption by 11%, and that led to a fuel savings of approximately 70,000 liters per year per truck, which would be approximately $55,000 US, and reduced unloading time. So this is just one real-world example of how EDEM provides the necessary toolkit to VR Steel to perform virtual repetitive testing, resulting in significant cost savings for the company. It also gave VR Steel a distinct market advantage as they were able to quickly design and test a new load body that outperforms competitors' designs. In this final example, EDEM is coupled with OptiStruct. Here, EDEM loads are used as input data in OptiStruct for an FEA analysis. EDEM can be used to export the forces acting on the truck body, and OptiStruct uses the information to plot the displacement on the truck body caused by those forces. You can also analyze the parts of the truck body that are most susceptible to wear, as well as obtain the reaction forces acting on the system. Shifting to a different application, another application for EDEM is mobile crushers. EDEM can be used to understand the mechanics of particle crushing and the spatial distribution of wear on a liner. By understanding how the bulk material interacts with the crushers, it's possible to optimize the design, performance, and durability of the crusher. This video shows an example of the jaw crusher mechanism inside a mobile crusher. In this case, EDEM can be used to understand particle breakage. By using EDEM's built-in breakage model, engineers can not only optimize their process for different materials, but also for different particle size distributions. By coloring the particles according to their size, it's possible to visualize how particles break. It is also possible to color particles based on compressive forces acting on them. Finally, it is possible to analyze the mass flow rate at the end of the crusher by using a mass flow sensor. Another common application for EDEM includes excavators. An excavator digging through a pile of rocks will require a stronger bucket and much more power than for a pile of dry sand. And designers also have to then account for different deformations on the bucket arm due to the loading. The level of wear on the bucket may also vary based on whether a material is abrasive, like sandstone, or less abrasive, like a soft soil. As with a dump truck, EDEM allows you to analyze forces during the procedure, investigate things like loading, discharging, spillage. You can visualize all of these and test and compare different designs or material options to identify the areas prone to things like spillage, material buildup, and wear. As buckets can have quite complicated motion, you can couple to an MBD package and allow those packages to control the motion whilst still experiencing the forces from EDEM. In this first example was completed using EDEM alone and shows that you don't have to couple with an MBD software to account for geometry motions within EDEM. You can add translations and rotations to any geometry and achieve quite complex motions if you don't want to use additional software. You can investigate the forces on the bucket for different materials, for example, small rocks versus large rocks. Or you could look at the mass in the bucket over time to investigate spillage. It's also possible to analyze and predict wear on the bucket to identify areas that will experience more wear. Or perhaps the total mass of material contained within the bucket, which you could alter by changing the angle of attack, penetration depth, or speed of the bucket. Or you could just visualize different material behaviors to see how they interact with the bucket. For example, a coarse rock versus a finer gravel, and how they fill into and flow around the bucket. Here's another example of an excavator. In this example, the challenge is to understand how the components within the boom arm will perform when going through a digging operation in different materials. In this case, a heavy, sticky iron ore, and alternatively, a lighter coal material that has less resistance to shearing. For this analysis, the hydraulic actuators were modeled in Activate, and the motion of the boom was defined in Motion Solve, based on the loads generated by the hydraulic actuator and the resultant loads exerted by the bulk material in EDEM on the bucket. During the simulation, information is continuously being passed between EDEM and Motion Solve and Activate. In terms of the model setup, there are several key components within the system. The first is the section that makes up the boom arm. These are represented in the simulation as flex body parts within Motion Solve, which allow for the calculation of stress in the boom throughout its movement. Next, there's the bulk material, which is being modeled in EDEM. And finally, the hydraulic actuators are represented using Altair's Activate. By linking the softwares together, we get a holistic model that captures all of the components of the excavator. Much like the excavator example, EDEM can be used in a similar manner to analyze and understand the loading on dozer blades. You can easily compare different designs by replacing or adapting geometries to attain high fidelity forces on the blade, which can then be used to calculate power requirements. In this video, you can see the dozer blade in action and the type of analysis possible. After the dozer has finished its traverse of the material bed, the data is then time analyzed in an FEA package. So first of all, we can see the loading profile, then the deformation that this might cause, and finally, the critical stress acting on the blade. The same analysis techniques can be applied to loaders. You can look at forces for different materials or different designs to identify spillage risks or optimize the amount of material that can be loaded. You could look at how different materials interact with a loader, both with the bucket itself and the entire machine, making sure that when you try to lift a more dense or heavier material, the loader won't flip over or topple over. Since the motion of a loader could be quite complex, you might want to couple with an MBD package for this. And over the next two slides, I'll show you examples of these. The first part of this video shows how our customers can create photorealistic renderings of their physics-based simulations. In this example, 4 Altair tools were used. EDEM for the bulk material interaction, Motion Solve for the multi-body dynamics, Activate for the 1D control of the hydraulic actuators, and PSIM to simulate the electric drivetrain. The focus of this presentation is the ability to model different bulk materials in EDEM. Thus, I will not go into details about how this model was set up. If you're interested in learning more about this modeling methodology, please let us know and we can set up a dedicated webinar on this topic. In this video, the video considers the digging and unloading cycle of a 4-wheel drive loader for 2 different materials. The loader itself contains a network of linkages and hydraulics, which creates a complex interaction between the machines and the material. To understand how different materials affect the loads acting on the system during operation, we are coupling EDEM with an MBD code. And in fact, in this case, it was Recordine. Here we are looking at the forces acting on the bucket for a heavy sticky material, and then for a light dry material. For example, looking at the height of the front axle, you can see how the material affects the motion as it drives up onto the pile. Or alternatively, looking at the force in the bucket hydraulic actuator. Another example of using an EDEM MBD coupling is one of a skid loader digging into an unconstrained pile of two different materials, which in this case is gravel on the left and wood chips on the right. You can see how the skid steer reacts to the material piles. First, the loss of traction, particularly in the gravel pile, as the skid loader digs into the pile, and then the response from the loading arms as the material is carried out of the pile. The wood chips are lighter than the gravel, and you can really see the impact that this has on the pile behaviors, with particularly complex material responses being shown by the wood chips that can be predicted with accuracy using EDEM. Slightly different application. We can utilize EDEM for modeling road construction equipment, such as a grader, here using EDEM only. This video, produced in collaboration with XCMG, shows how EDEM can be used to simulate grader applications such as flattening, ditching, and scraping. Here, ground particles are colored based on velocity. Alternatively, we can color the particles by layer so that we can examine how different layers mix or interact with each other for a flattening and a ditching operation. And we can also color the particles based on the height or the position of the particle and how they move over time as the material is scraped away. Additionally, data for the grader blade relating to wear, pressure, and forces can be obtained, allowing for optimization of the piece of equipment. So in this case, for a ditching application, we can see the pressure profile based on the coloring of the blade, where some of the particles on the blade are hidden. And then total force on the blade for the scraping example. Also coloring on the blade based on the distribution of the forces. Finally, here we can look at the mass of material that has been removed from the wall as the grader moves past it. Now we have a compactor, which is another example of EDEM being used to simulate road equipment. In this case, EDEM can be used to analyze the compaction process by analyzing things like the bed porosity and solid fraction, as well as the forces acting on the drum. Here, the porosity is analyzed in 3 different locations of the bed using an EDEM tool called a grid bin. In these grid bins here, these 3 slices are represented in the full length of the particle bed shown on the top. And we're displaying porosity from 100% in red down to 11% in blue. Alternatively, in EDEM, you can visualize your results as a continuum analysis. And that's what's shown in the bottom left here, with porosity ranging from 100% or no particles in red to the densest or lowest porosity in blue. In this let me back up. One more try. In this video, we can see the roll's velocity as it moves over the soil bed. We can see that only the particles that are on the top layer are really affected by the roll. And I'm saying that based on the fact that the red particles that have a velocity of approximately 0.18 meters per second are all constrained to adjacent to the compactor. This allows engineers to understand soil behavior, particularly along the depth of the soil axis. It's also possible, as in the dump truck example, to analyze regions of the roll that are more likely to wear and how the stresses are distributed along the roll. And that tangential energy that's been absorbed by the surface of the roll is visualized in the bottom left. Switching applications again, we've got grab buckets. Grab buckets are a type of equipment used to unload dry bulk cargo vessels. Grabbing dry bulk material such as iron ore or coal from the vessel and transferring the grabbed material to a hopper on the quay. Development of grabs is still a complicated process, as predicting the performance of a new design is hard and involves building physical prototypes, which is expensive, time-consuming, and limiting. It's hard to understand what happens inside the grab. On the left, this grab developed by NEMAG was designed using EDEM coupled with MBD. The patented NEMAX grab combines lower dead weight and a higher payload with shorter closing times, leading to great improvements in efficiency with a vessel that unloads in 10% less time, which is a big deal if you understand the cost of having a vessel in the port. On the right, let's look at it in more detail at an example that was done in EDEM and MotionSolve to model the grabbing. By coupling EDEM with MotionSolve and Activate, we can model the forces and torques acting on the winch and also the force acting on the cable over time for a fine material and a coarse material. You can see here that we have a different force and torque response depending on the bulk material that's being modeled due to the variations of the characteristics of that material model. So on the top plot, looking at the actuator force, the force to close the grab, you can see that the peak force of the coarse material is considerably greater than 300% larger than the fine material. Alternatively, on the winch, you can see that the fine material has a peak torque that's slightly larger initially and has approximately a 12% difference once it's being lifted out of the container. And finally, the cable force, regardless of the material, is quite similar. We can also analyze the efficiency of filling the grabs with different bulk material. Here we have a fine and coarse material again, so you can see that with the fine material, the grab is able to contain a higher mass than the coarse material. And we also see that the fine material has a loss of about 1 kilogram due to spillage during the movement of the bucket, whereas with the coarse material, we have a greater amount of spillage due also for the grab's inability to close on the coarser particles. We can easily determine bucket system performance by operating with different materials. In this example, we can see how the stresses are distributed on the bucket arm when handling fine and coarse material. We see that the coarse material will transmit higher stresses to the critical components. And by coupling EDEM with OptiStruct, we're able to improve durability of equipment by reducing hotspots and stress concentrations. properly size the cable system, and design the equipment to handle different materials while not over-engineering it. In our last example here, we can see how 3 of Altair's softwares were used to optimize a bulk solid mixer. The geometry of the mixer was defined parametrically in Altair Inspire. EDEM was used to simulate the interactions of the 2-part bulk mixture with the mixer. Altair Hyperstudy was used to generate the DOE, or design of experiment, and execute the optimization. And finally, the EDEM simulations were run on a HPC, the Altair Unlimited Cloud, to provide accelerated simulation results. The parameters optimized here were the paddle angle, paddle width, paddle pattern, which would be the number of paddles per row and per column. And the key performance indicators were mixing quality, and energy consumption, throughput, and equipment cost. You can visualize the evolution of the optimization as Hyperstudy completes the EDEM simulations here. And finally, you can see how the optimum design was able to achieve an improved mixing level while maintaining throughput. Their baseline on the left and the optimized on the right, the 27% improved mixing efficiency. Though a bulk solids mixer might not be considered a piece of construction and/or mining equipment, I've included it here to highlight the ability of leveraging a suite of Altair tools to optimize designs. And the important thing to take away here is that this methodology can be applied to any application. And though I didn't talk about it during the material calibration phase, the combination of EDEM and Hyperstudy can also be leveraged for the calibration of material models. It's a very powerful tool that can be used for more than just geometry optimization. So in summary, Altair simulation software can be used in the design of construction and mining equipment to help engineers understand how different materials affect designs, predict bulk material behavior, which can help you identify the risk of blockages, spillage, and areas of high wear, can perform virtual repetitive testing, allowing you to simulate the same conditions every time. And the important part there is you can, say, investigate the effect of design changes and be sure that the design change is causing any difference in the response, and it's not a material variation that's causing the response. Improve the reliability of the machine and the equipment and design for, say, worst case scenarios. Shorten the entire design cycle by reducing the number of prototyping stages. And finally, optimize the equipment performance. That is all that I wanted to cover today. I hope that it has been useful to you and given you some insights into various Altair technologies and how it can help in designing construction in mining equipment. And I would be happy to answer any of your questions at this time.
Thanks so much for running through that, Eric. Just feel free to send questions now in chat. There's just a couple of questions I sometimes get, I figured it'd be good to ask you. Can you touch on just how EDEM utilizes GPU versus CPU for solving? That's a common question I hear a lot.
Sure, yeah, absolutely. So for the solving of DEM simulations, they're typically quite heavy. They're computationally heavy. And EDEM has invested a lot into improving the solve speed or the performance of the solver. And a lot of that has come with the improvements to not only the available hardware, the GPU hardware, but also the algorithms that are being used to solve on a GPU. So if you would have performed a DEM simulation 10 years ago, you likely would have been forced to do your solves on a CPU, and you could maybe expect to have a few thousand particles in your simulation and have those run on the order of perhaps hours to days to complete, depending on the duration of your simulation. And now with GPU solving, if you say pick the highest performance GPU, it would be reasonable to have millions of particles, tens of millions of particles even, and have solve times with such a large domain that's even less, like it could be minutes, hours, or even days to complete. So the GPU solving in general, I would say, is a multiplier on the order of orders of magnitude faster.
That makes sense. Appreciate that, Eric. One of the cool things you're running through is a lot of the coupling with some of these other tools. With a license of EDEM, do users get access to some of these other tools like AccuSolve and HyperWorks and MotionSolve?
Yeah, that's a great question. And honestly, I'm maybe not the best person to answer this question. So take my answer perhaps with a little bit of a grain of salt. But basically, the way that the Altair licenses work is that, say if you're solving an EDEM simulation, I think that takes, if it's a GPU simulation, 60 units. And say if you wanted to couple an EDEM simulation with a multi-body dynamic simulation, I gave a number of examples of those, say the wheel loader or the excavator, that MotionSolve token usage is less. I don't know the exact number, but for a single user on a single machine, if I'm using EDEM alone or EDEM coupled with a simulation, I will basically pull the same number of licenses as if I was just solving the EDEM simulation alone. Something that we refer to as either stacking or leveling. In this case, the license token requirement levels, it doesn't stack. Does that make sense?
It does. Yeah, thanks so much, Eric. Is there any other questions from anybody still here? I know we have mostly everyone's still here. Before we wrap up. I think that's everything, Eric. Thank you again so much for leading this webinar. I think it was very insightful. And for those of you attending, keep an eye out for some future webinars, both on the Altair end and then also on the True Insight end. We are probably going to definitely be running some more webinars in the coming months, and Altair will as well. If you do have any questions about anything further, I'm going to paste my information in the chat, and I can reach out to Eric if you guys do have any questions. But thanks again, Eric, for running this.
Yeah, thank you, Drew, and thanks for hosting the webinar.